Okay, welcome back, everybody. Moving on to one of my favorite sections in the book. We're kind of concluding it in many ways, but these last few sections really are my favorite. We've been working really hard to give ourselves the tools so we can handle some of these arcane topics, such as chaos. And so today's our first day on chaos, and in particular, the subset of chaos that we're going to be studying today is this so-called sensitivity to initial conditions. A lot of you probably have heard of this as the butterfly effect, and the mathematical term that we often use to describe a sensitivity to initial conditions is Lyapunov exponents. So there's another fun name for everybody to memorize. Lyapunov, Alexander Lyapunov. He was I believe, Russian mathematician in the early 1900s, and he had a lot of really, really good things to say about chaos and really dynamics in general, as well as stability. So actually, we could have taken a Lyapunov approach to stability in the previous section, but we didn't. Anyway, here we're stuck. We have to take the Lyapunov approach. And before we get into it too much, let's talk about chaos as a whole. And chaos in continuous time dynamics, my definition, this is something that's important to recall, is that the mathematics community as a whole doesn't have a definition that everybody agrees upon, but a very common one is a definition by a man known as Devaney. Definition. And Devaney's definition is the one that we're using here as well. And so this definition of chaos, as applied to a continuous time dynamics, is we're going to start with a continuous time dynamics, and we can initialize it anywhere. But we say that this exhibits chaos. We can also use chaotic behavior or is a chaotic dynamics. And it's allowed to exhibit chaos only in a region, right? So we're not requiring that this thing is fully chaotic everywhere. We're allowed to restrict ourselves to a region and say it's chaotic within some region omega, if within that region we're sensitive to initial conditions, which is kind of the section of, or the idea of this section. And I've linked the definition there. We are topologically transitive, and that's going to be in the next section, section 13.3 within omega. And then we contain dense within omega periodic points, and that's also going to be in section 13.3. So 2 and 3 we're going to save to section 13.3, but number 1, which is maybe the most excited part about chaos, it's the one that a lot of people think about, this sensitivity to initial conditions, that's going to be in our current section, 13.2. And in particular, we're going to try to define this thing called the Lyapunov exponent, which is what we really need to have a sensitivity like this. Well, anyway, to kind of head into the rest of these sections, and actually the rest of this book, is the following definition. So I really want all of you to take a good amount of time to figure out what this definition is saying, because the rest of the book relies very heavily on this definition. Okay, so this definition is the definition of a flow map. Okay, sometimes we'll just call it a flow. That's a little bit ambiguous and maybe a bad way to talk about it, because it is a map. It's mapping the flow. But what it is it's a function, and actually it's a vector field. Okay, because I'm starting with a vector and I'm ending with a vector, a d-dimensional vector, and it's parameterized by time greater than t naught. Okay. So that's why I'm putting a subscript t comma t naught by it. You'll see a lot of different notations for this sort of flow. Usually they're all similar. You'll either have phi to the power t or a phi subscript t. And a lot of times people will omit t naught because they'll just initialize at 0. Okay, so if you put a 0 in there, a lot of people will just omit t naught for that. But because I want to be a little general and just say we can initialize anywhere, I write phi sub t comma t naught to say, okay, where have we initialized? Where are we now? That's kind of the idea of t and t naught. And it's a vector field. So it takes in x, a vector, and it outputs a vector as well. And this vector, so the vector output at time t, the vector output at time t is y, where that specific y is actually the solution to my dynamics initialized at x. Okay, so whatever vector I'm plugging into the flow map, that's the initial point of the dynamics. And then I basically say, okay, my dynamics is allowed to push me somewhere at time t. If I wait, 20 seconds, my dynamics pushes me somewhere. And then I say, wherever that's pushed me, that's the output of the flow map. So more or less, the flow map is just a reinterpretation of this dynamics, where, let's say it's a reinterpretation of dynamics where the variable is the initial condition, and in particular, like the initial spatial condition, right? Let's say spatial. So it's a reinterpretation of the dynamics where my variable, which goes into the flow map, is the initial condition of my dynamics, and then the parameterized part of my flow map is the time that I've waited. So maybe I fix a time 30 seconds. I say there's a map that takes me from an initial condition to wherever it ends up after 30 seconds. That's a perfectly well-defined map from a vector to a vector. And so let's look at the next dynamics here. This is a nice example of just, a single dimensional nonlinear dynamics. And you'll notice that I've decided to initialize at x here. And that's because I'm going to construct the flow map to this, right? So the way we construct a flow map by solving the dynamics for an arbitrary initial condition x. And that's how we're gonna, so if we solve this, we end up with, well, traditionally we would solve it and we would say that this is y of t, it's the solution to the dynamics. But you'll notice that when I write it like this, if I write it as y of t, I'm emphasizing that time is my variable. The flow map is the understanding that time is now a parameter, and actually the initial condition, x, is the variable. So that's all the idea is the flow map is reinterpreting the initial condition as the variable of the map. So that's how I find my flow map. You can verify it here, right, by actually computing the time derivative, and then you'll notice that it solves the IVP. Okay, but why do we care about a flow map? At least in this section. There's lots of reasons why we care about the flow maps. They're going to be one of the most useful tools in the study of nonlinear dynamics for the rest of our book. But why we care about it for this section is that we can actually think about, okay, suppose I initialize my dynamics at x1 and I initialize my dynamics at x2. Then the difference in the flow maps for some time, some future time t, that difference describes the distance between the futures, right? I can compute the kind of the spread. This is the spread of x1 and x2 over time. So that difference describes the spread of two initial conditions over time. We can think about saying, okay, what about the spread of two initial conditions infinitesimally close to each other? If I think about the spread of two initial conditions infinitesimally close to each other, actually we can compute what that is, an infinitesimal, by just computing the Jacobian, right? The Jacobian matrix of this flow. And we get away with that because now it's a vector field, right? We can compute derivatives in space because we're interpreting this as a function of space. And so we can compute the spread of two initial conditions infinitesimally close by really, it's the Jacobian, right? But then it's acting on, okay, that's the direction of the spread, right? dx is the direction of infinitesimal spread. So I look at the Jacobian of my flow map at some time t, and I act that vector, or that matrix on the vector which describes infinitesimal spread, and I recover actually how the spread would evolve over time of 2 points infinitesimally close to each other. Now you can probably see where I'm going, right? Because if I have some notion for which 2 points infinitesimally close to each other spread really far apart, that's precisely sensitivity to initial conditions, right? If I think about if 2 points infinitesimally close to each other, infinitesimally close, spread a lot, then I am sensitive to those, I'll say that, even to that initial condition. Right, because I'm sensitive to this point x. That point x is really sensitive because even if I'm infinitesimally close to it, and I'm somewhere else though, I'm just like pushed off of it an infinitesimal amount. If the spread of those two x's is big over time, then that's what sensitivity to initial conditions is. It's basically saying, okay, I start here, I start really close to it, but maybe the flow takes me in that direction for one of them and in that direction for the other. If I have flows like that, that's what it would be to be sensitive. But then let's think about maybe quantifying this, right? So to quantify this, we need to understand the Jacobian. We really want to understand this Jacobian of the flow somehow, and we can understand it using this specific matrix-valued initial value problem. So here I have a matrix-valued initial value problem, and it says that the temporal change of this Jacobian, which is a matrix, is equal to actually the Jacobian of n, where n here is the n from my dynamics, scrolling all the way up here. Right, the n is the n on the right-hand side of my dynamics, the nonlinear term. And I'm going to take the Jacobian of the nonlinear term, and I'm evaluating it at the flow. Okay, so this is the Jacobian matrix of nonlinear n in dynamics, y prime equals ny, y at t0 equals y0. So it's that n. I take the Jacobian, but I evaluate the Jacobian evaluated at phi sub t comma t0, the flow. Okay, and then that's a matrix which acts on my Jacobian of my flow. Okay, so this is saying that the time change of the Jacobian of the flow is actually the Jacobian of n evaluated at the flow acting on the matrix, which is the Jacobian of the flow. And in fact, I initialize at the identity matrix. Okay, so this is an IVP which really easily describes the behavior of the Jacobian of the flow. Now, unfortunately, this IVP isn't terribly well defined, because if we don't know this, if we can't solve for this, it's not easy to solve the IVP. And in fact, this is a nice remark, in fact, if we could solve for phi sub t comma t0 of x, then we could just compute d phi t0 directly. Okay, so why is this equation even useful? Well, sometimes you might have some bounds you can place on that matrix, and if you have some bounds you can place on that matrix, then you can solve this equation at least in some bounded sense. And so you can talk about qualitative properties of the Jacobian of the flow without necessarily having to solve for the true flow. And so that's why this equation is actually useful. I have a proof of it. The proof is not terribly difficult. You just kind of re-represent the flow and take a Jacobian of it. All right, so now we have this idea of the Jacobian of the flow, and now we're almost ready to get to the point of sensitivity to initial conditions. We have this notion of a Lyapunov spectrum. So this is probably the most important definition you can memorize from this section, aside from the definition of the flow, because the Lyapunov spectrum is how we're going to verify. This is how we verify sensitivity. Okay, so we verify sensitivity by constructing a matrix, which we call lambda sub x. Lambda, I believe, for Lyapunov, sub x for it's specific to a point at which you start. And this matrix is going to be the limit at infinity of the matrix logarithm where, jump back to chapter 2 to recall how you calculate matrix logarithms with, Jordan form, etc. So jump back to chapter 2 for that. So we're going to take a matrix logarithm of the Jacobian of the flow, transpose, multiply by the Jacobian of the flow, and then we're going to divide that matrix by 2t and take t out to infinity. That's going to be called the Lyapunov matrix. And the spectrum of that matrix, which you'll recall that a spectrum, also from chapter 2, this section relies on chapter 2 a lot, spectrum equals sigma equals the set of eigenvalues. Okay, so I'm just going to compute all of the eigenvalues of the matrix. That set of eigenvalues is my spectrum, and if my matrix in particular is this matrix, then I have what I call the Lyapunov spectrum. Okay, and that Lyapunov spectrum starts at x, because actually these flows were supposed to be on x here. So those flows are flows on the initial condition x. So let's look at maybe calculating one of these. In a one-dimensional setting, right, this matrix will just be a one-by-one matrix, and so things get a little bit easy. But we'll go ahead and do it. And so we'll calculate the Lyapunov spectrum for this dynamics, y prime is y squared, and we initialize at x. And we've already seen today that the flow map, and I dropped t0 there because I'm initializing at 0. We've already seen that the flow map is just x divided by 1 minus xt, which means taking a Jacobian in one dimension is just a partial derivative with respect to x. That Jacobian, take a partial derivative with respect to x, we get the following, right? And so now to calculate the Lyapunov spectrum, now that I have this, when you have the Jacobian of a flow, the Lyapunov spectrum, recall, is I'm going to take the limit as t goes to infinity of the log of the transpose of the Jacobian times the Jacobian divided by 2t. And so I'm going to take that, I'm going to transpose it, but we interpret, right? So interpret this as a 1-by-1 matrix. So for a 1 by 1 matrix, it is its own transpose. So basically I'm multiplying it by itself, so I'll square it. I'm going to take the log of that function squared, and I'm going to divide by 2t. So there we go. There I have it. I take the log of the function squared, and I divide by 2t. If I simplify that, the 2 with properties of logs, my 2t can come over here as a 1 divided by exponent. So I'm going to be taking this to the 1 over t power. One more log rule pulls out a negative 2. And I actually have 1 minus xt to the 1 over t. Now this is maybe a little unclear how we would compute the limit as t goes to infinity of this. But jumping back to the first time you encountered e, in fact, the first time you encountered e, you encountered it probably as continuously compounded interest. And you saw that the limit as n went to infinity of 1 plus x over n to the nth power was e to the negative x, or e to the positive x, and then if I just put a negative sign in front of x, I get e to the negative x, and that's actually what's happening here with this limit. And so we're getting a negative 2 times the log of e to the negative x, which ends up being the log and the e cancel, and we get 2x out of this. Okay, so 2x is our Lyapunov matrix. This is lambda sub x as a matrix, a 1 by 1 matrix, but the spectrum of a 1 by 1 matrix is just the number itself, right? And so that spectrum is 2x. And so I have a Lyapunov spectrum for this dynamics, and I've calculated it as 2x. We can then add an extra condition onto our spectrum, and this is called the maximal or top Lyapunov exponent. And it's simply the maximum value within the Lyapunov spectrum. So we're just looking at the top value in the Lyapunov spectrum. And why that's important is that this next remark refers to the fact that the Lyapunov spectrum represents a rate of exponential spread. So if I have 2 points infinitely close together, they spread apart exponentially fast. And that's what the Lyapunov spectrum represents. In fact, then the top Lyapunov exponent describes the most exponential spread you can possibly achieve. And so what we get out of this is we define sensitivity to initial conditions as if the maximal Lyapunov exponent is positive, strictly positive, we call ourselves sensitive to initial conditions at that point, and in fact near that point because of the way continuous functions work. And so sensitivity to initial conditions, mathematically speaking, is all dependent on this number, lambda max, which we have defined as the very top number in the eigenvalues of that Lyapunov matrix, or it's the very top number in the spectrum of the Lyapunov matrix. That's what it would mean to be sensitive to initial conditions. Now there are some nice extra properties here. If we decide that for every x in some region, it stays positive, right? Because it depends on x, but if it stays positive within a region, then we call ourselves sensitive to initial conditions within the region. And finally, if we never go negative, right, or we never even reach 0, this would basically say the smallest top eigenvalue over all of space, that's what this is saying. If that's never 0, then globally, the entire space is sensitive to initial conditions. And so we jump back to this nice dynamics we've been working with so far today, and I jump up here to where we calculated the Lyapunov spectrum of that dynamics. We got 2x out of it. So if I look at the Lyapunov spectrum of this dynamics, actually I have that lambda max, which is the top eigenvalue in the set 2x. The top eigenvalue there was 2x. And so we see that we're sensitive to initial conditions for all positive x. And so it's only positive x where we're sensitive to initial conditions. In fact, we're not sensitive to initial conditions when x is less than or equal to 0. And we can actually see this graphically. Maybe I should have included a graph in the book, but for now we can just include this graphically. If I initialize somewhere positive, suppose I initialize at 1, then my dynamics, this is the time axis, my dynamics actually reaches an asymptote at t equals 1. And if I initialize at like 1/2, that's a 1. 1/2, then actually I don't reach an asymptote until t equals 2. Okay, well what that means is if I'm really, really close to 1, let's say I started at 1 minus epsilon, I actually reach an asymptote at t equals something like 1 over 1 minus epsilon, where that's a future time that's substantially farther forward than where I started. And so this spread right there, the spread between the two of them does grow exponentially fast. And that's why I'm sensitive to initial conditions near 1, near actually any positive x point, right? And if you solved this instead, if you solved the solutions for some negative values of x, there's my time axis, and suppose I started at -1, what we actually see is we approach 0 over time, which means that suppose I started here at 1 minus epsilon and I still approach 0 over time, there's no exponential spread between those 2 points, right? And since there's no exponential spread between those 2 points, then then I don't have sensitivity to initial conditions. So that's how we can like quantitatively talk about the spread between initial conditions is with this top Lyapunov exponent. And we can talk about sensitivity within regions of where we start, where we initialize. The next proposition is really important. I actually leave the proof as an exercise to you. But this is a very important proposition because it's saying that chaos and sensitivity to initial conditions, even the butterfly effect, right? So chaos and the butterfly effect are not the same thing. One is a subset of the other because linear initial value problems are often sensitive to initial conditions. If I take any linear IVP, now these are your classic linear IVPs, which you have a solution, right? Your solution is e to the tm acting on y0. If whatever eigenvalue of my matrix M I have, that's actually the maximal Lyapunov exponent. So the top eigenvalue of the matrix M is the top Lyapunov exponent, which means that a linear system exhibits sensitivity to initial conditions so long as the matrix has some positive eigenvalue in it. And so you can think about this in the sense of like the orange dropped in the upside down bowl, right? Because when we were dropping our orange in an upside down bowl the other day, my parabolic bowl, that was a perfectly linear system. Draw it out here again. So there's my upside down bowl. And if I drop an orange on it, if I drop the orange just to the right of the origin 0, my orange falls off over to the right infinitely, well, not exponentially fast. And if I draw my orange just to the left of the initial 0, 0, then my orange falls exponentially fast to the left. And so the spread of two oranges dropped near each other is exponential. I have an exponential spread dependent on the initial condition. And that's why, even linear systems, which are not chaotic at all, they're perfectly well behaved, but they can exhibit a sensitivity to initial conditions and they have a positive Lyapunov exponent. So that's just something to keep in mind when you're talking about chaos with some people, because they're going to be under the impression that sensitivity to initial conditions and chaos are the same thing, and they're not. You need sensitivity for chaos, but it's not strong enough to guarantee chaos. We need some other things to have chaos, and we'll see that in the next section when we tackle the rest of what chaos has. But I've provided an example of a slightly more difficult two-dimensional system where we can actually prove something about the Lyapunov exponents. And actually, I've given myself these numbers alpha and beta, which I'm leaving as arbitrary, so that we just reassure that the maximal Lyapunov exponent is actually greater than or equal to alpha squared plus beta squared. And so by starting with this dynamics and tuning alphas and betas in the whole dynamics, you have the choice over deciding what sort of exponential spread you might want in a two-dimensional system. And these are not easy to come by, so that's why I've provided this here. It's actually really hard to get some proofs on Lyapunov exponents, and a lot of people are getting their PhDs. They're getting papers in good journals out of just proving a single system has a positive Lyapunov exponent. So these are not easy things to prove. But we'll look at this dynamics, and I'll go through the procedure of maybe how we would calculate a Lyapunov exponent here, just so that you can all see what the procedure would be like. So what we're going to do to calculate the Lyapunov exponent, recall what we need. We need d phi sub t, because this is the Jacobian of the flow map, because my Lyapunov matrix lambda sub x is this limit, right? As t goes to infinity of the log of d phi t transpose d phi t all over 2t. And so to calculate this log, or this Lyapunov matrix, I really need an idea of what d phi t is. And so the first step I'm going to do is write down that proposition which describes how d phi t evolves. D phi t evolves as an initial value problem that satisfies this quantity, where n is everything up here, right? So I'm going to calculate a Jacobian of everything up there. And what I get as a Jacobian is the following. And that's actually a really nice Jacobian of my flow, because I was able to factor out all of the terms which depend on time. Right, the terms which depend on time I could factor out, and I'm just left with a matrix which doesn't depend on time, so that the initial value problem actually looks like something that corollary 6.5.7 can solve. This was one of the corollaries of the Magnus expansion in the specific case, when you could factor out all of your functions which depend on time. And so because of that, we actually have a nice expression for the Jacobian of the flow, and it looks like an exponential with a matrix in it, right? The matrix exponential, and then I'm just left with this integral of kind of the terms related to the flow. They're not exactly the flow, but they're related to the flow. And what we can do with that expression then is actually compute the Lyapunov spectrum. So I've already put it inside of sigma. I'm just saying I'm calculating the spectrum now. But if I'm calculating the Lyapunov matrix lambda, I take this expression for d phi t, I'm going to take its transpose, and we're lucky enough that it's the same because our matrix here is symmetric, and so this matrix exponential is also symmetric. And so using some nice logarithm identities. I can convert this now it's the Jacobian of the flow to the 1 over t power. And you'll notice if I take this exponential to the 1 over t power, I really just have a 1 over t sitting around in front of the exponential. And also if I take a log, remember it's a matrix logarithm of a matrix exponential, the log of that matrix exponential will just give me this expression. And that expression is easy enough to calculate because, or at least estimate, because sigma I can just bring, thanks to the spectral mapping theorem, make sure you can check that theorem out again. Sigma I can just bring over to the matrix. So I'm computing the spectrum of that matrix, and then I'm going to estimate this from below. So this is the average value of this expression over time, right, over all of time. The average value of that expression, well, the minimum value that expression can take is 1 because it has a 1 plus something squared out front. And so it's estimated from below. This has to be greater than or equal to 1. This expression. And so I take the spectrum of that matrix, and I know that the limit is greater than or equal to 1, which gives me the Lyapunov terms, where my Lyapunov spectrum is alpha squared plus beta squared, or 0, and then of course the top Lyapunov exponent is alpha squared plus beta squared times this average value, which I know is greater than or equal to 1. And so lambda max is greater than or equal to alpha squared plus beta squared, which will always be positive so long as these two are non-zero real numbers. And so that's how we can actually estimate a Lyapunov exponent without having to solve the actual flow. So all of a sudden I know, by doing those calculations, I already know that this dynamics is sensitive to initial conditions. Even though I haven't solved the dynamics, I know that it's sensitive to initial conditions. With a specific sensitivity, alpha squared plus beta squared, without having to solve the actual ODE. And I'm not entirely sure I could solve the actual ODE, right? This is not exactly an easy ODE to solve. And so we can gain some very quantitative behavioral estimates on nonlinear problems without having to solve nonlinear problems exactly. Anyway, I hope you enjoyed that section. This is one of my favorite sections. It's really, really cool to think about how we can quantify a sensitivity to initial conditions. The next section we'll be covering the rest of the ideas with chaos. Anyway, I'll see you then. Bye.